Hey, welcome to Central Limit Theorem. This is lecture 6 and we are ready to rock. Quiz 6 will be due on Friday, so you'll have quiz 5.5 and quiz 6. And don't forget there's the special double quiz, which is just meant to put you in a testing situation. So far we've had take-home quizzes and we've gotten hopefully really good at it, or we're going to get better at it by Friday. Double quizzes don't count nearly as much as tests, so you shouldn't be too stressed out about it, but it is an opportunity to see exactly how much we know. And then the following week we can really press and fill in the blanks. But right now we're going to fill in a big blank, which is known as the central limit theorem. Here we go. So far what we've done is we've done the normal distribution. So if you can remember, right, we started off with some sort of normal distribution. And we said, hey, let's let mu equal 10 and sigma equal 2. This is exactly what we've been doing for the last couple of days, so just a review. And we said, hey, if it's normally distributed, it must have mu of 10, standard deviation of 2. I can list them all on here. But let's say I want to know the probability that x, which x is just some shoe size, let's say this is a distribution of shoe sizes, that x is less than, say, 12. Let's say that that's what I'd like to do. So if I want to do that, then of course what I'm going to have to do is change this into a z, right? Because we know the distribution of the z's and we have a table for that. So here's probability x is less than 12. We need to get to the table of probability so we can figure it out. But first what I'm going to do is draw and shade. So if that's 12, then I'm going to shade. That's the probability that I'm looking for. And that's what you did on class on Monday. So the next step is, of course, to transform that, or just simply find its z-score. And remember, if I'm looking for a z-score, that z equals x minus mu divided by sigma. So for this 12, you can do this one in your head, but because we know that it's one standard deviation bigger than the mean. But if I wanted to find it, that would be x here is 12 minus mu, which I've said is 10, divided by sigma, which is 2. So that leaves this being 2 divided by 2, which of course equals 1. So this has a z-score, 12 has a z-score of 1, and I'm trying to find the probability of being less than 12, which we just said is the same as the probability of z being less than 1. of z being less than 1. I don't have a table for that, but I do have a table for the z's. That's the standard normal table that I had before. So the probability that z is less than 1, if we looked at it in our table, should be about 0.8413. And that's what we've done. Notice how after you've done this a bunch of times, it's just a review, after you've done this a bunch of times, you see that we have the ability to find probabilities of normal distributions. But let's come on over here. So if we have that normal distribution, we can find the probabilities. But what happens if, say, the originals have a mu of 10 and a standard deviation of 2, but they don't have the shape of the normal distribution? So it's just something like this, some amorphous distribution. Things can be distributed however. I wouldn't think that this would be the distribution of shoe sizes, but if it was, you know that the area under the curve is still equal to 1. The curve can't go below the x-axis here. So the area under there is 1, but it's not normal. So if I was trying to approximate this using a normal distribution, you can see, let's say that I want to find the probability, let's say that that's 10 right there. Again, every distribution, nearly every distribution has a mean and a standard deviation. That has the mean and standard deviation, same as the normal distribution, but it's not normally shaped. So again, if I was trying to find the probability of being, say, less than that, but I was trying to approximate it with a normal distribution, surely you can see, so they both have this, I should have drawn that kind of there, have a mean at 10. Both have a mean at 10, but notice that the normal distribution is not going to be a good approximation, right? It's going to way underestimate the true probability because it doesn't follow a normal distribution. So that's going to be interesting. So let's go ahead and erase that idea. Let's draw our amorphous distribution back there. And let me tell you the central limit theorem. We've gone kind of around. Here comes the central limit theorem. It says that no matter what the distribution, I'm going to write this of x's, no matter what the distribution of the original individuals, the original distribution, which is not normal in this case. If I then sample, let's just say I sample n equal 30. So I'm going to sample 30 of these guys from here. So most of them will be in here. Occasionally you'll get one out there, but it's lower, so you wouldn't get it very often. Most people I sample will be in here. If I take 30, and then I take the average of those 30. If I take the average of those 30, let's say that that average, it's probably going to be somewhere close to the population average, but let's say that it turns out to be 10.4. Great. So that's what I did. I just pulled 30, and I got X1. Now let's say, this is the key point, let's say that I pulled another sample of size 30. If I pulled another sample of size 30 and took their average, so here I go again, I pull 30, I take their average, I call that X bar 2. I've done it twice. I don't expect it to be the same as 10.4. It's a different set of 30 people. They all come from the same distribution, but it's just a different sample. So this one might be something like 9.8. And let's say I drew another of 30. So this is my third sample. I've essentially sampled 90 people. There's 30 in there in that average, 30 in there in that average. This guy is like 10.8, and I could do that a bunch of times. So let's say that I do it 1,000 times. And every once in a while, right? Every once in a while, you're going to get something, you're going to randomly pull every once in a while somebody from over here. And that will be, say that this becomes like a 13.0, but it's not going to happen very often. Most of the time, let's go even up to X bar 1500. Most of the time, it's going to be around, I don't know, 10.2, 10.1. So notice they're all different, which means there is a mean of all of these numbers. It would be a mean of means. Anytime you've got numbers that are differing, they have a standard deviation, which means they have a distribution. What is the distribution not of X, but the distribution of these X bars? Sure does look like most of them are somewhere around 10. And again, occasionally you're going to get a big one here at 13. Occasionally you're going to pull all the 30 from here. So maybe X bar 999, maybe that's equal to 8.1, a little bit farther. But on average, they're going to be around 10. And this is the central limit theorem. It says if you take samples that are big enough, no matter what the individual distribution, which I have no idea how to find probabilities for, the means will be normally distributed, which means we can use our framework and our table for the z distribution, because the averages, these averages will be normally distributed, and they will be normally distributed with the same exact average, right? I can call this mu x and sigma x. It'll have the same exact average as the original distribution, which is huge, except, so I call that mu x bar, that's the mean of all these x bars, is equal to mu x, which is equal to 10. It's the same. But sigma x bar, what is the standard deviation of these guys? It's related to this standard deviation, but it's huge, pause, dramatic pause. It's related to the original standard deviation up here, but it's smaller by the factor of 1 over the square root of n. That is huge. This is the central limit theorem. Non-normal distribution changes into normal distributions for the averages, with a mean that is the same as the original distribution, but with a standard deviation which is smaller. And when the standard deviation shrinks, that means we have a more accurate estimate, because it's closer around 10 here. And this right here, for a matter of vocabulary, is known as the standard error. Wow, so that's the intro. That is the intro right here. In fact, you guys know this. So those of you who are kind of into the notation, this is X bar. We can say X bar has a normal distribution, but its distribution is the same as the originals, but the standard deviation, the X bars have a normal distribution. This is the central limit theorem right here, with the same mean as the original distribution, but with a smaller standard deviation. So you can feel free to pause it, rewind it. Of course, shoot me any emails with some questions. Please visit the office hours. We're going to go to a PowerPoint presentation next, but this is step 1. Whammo.